Hello students, I am Dr. Pragati Jadhav, and in last lecture we have seen the band structure in semiconductor. The next point of this module number 1 is carrier concentration at thermal equilibrium for intrinsic and doped semiconductor. So one has to know why there is need to study the carrier concentration. So there are some points, that is why we need this to understand this carrier concentration. The first point is when we are finding the electrical properties of semiconductor, we have to know the number of charge carriers per centimeter cube are available within the semiconductor. Then the second point, that is second need to study the carrier concentration, is that to analyze the semiconductor devices. Analyze the semiconductor devices. That is, one may find the semiconductor devices, how much the voltage is developed or how much current is flowing through the semiconductor devices. So we need to know the number of charge carriers available within the semiconductor, and so we have to need to study the carrier concentration. So in order to study the carrier concentration, one has to know the following points. In order to understand or study the carrier concentration, the first point is Fermi-Dirac distribution function. One has to know Fermi-Dirac distribution function. Distribution function. Second one is Fermi level, and the third one is electron hole concentration at equilibrium. Second one is the Fermi level. And third one is carrier concentration or electron and hole concentration electron and hole concentration at thermal equilibrium. At thermal equilibrium. So first we will see about the Fermi-Dirac distribution function. So as we know, the band structure in semiconductor in valence band, there are number of charge carriers, or valence band is totally filled and conduction band is totally empty. So this is valence band which is totally filled, and conduction band which is totally empty, and this distance between valence bandage and conduction bandage is nothing but the forbidden gap. Forbidden gap, which is denoted by Eg. So the distribution of electrons over a range of allowed energy levels is nothing but the Fermi-Dirac distribution function, and which is given by the function f of E, which is equal to 1 upon 1 plus e raised to E minus EF upon KT. So this formula gives the Fermi distribution function, which gives the probability that the allowed energy levels are occupied by electrons, in which this K is nothing but the Boltzmann constant, which has the value 1.36 into 10 raised to minus 10 raised to minus 23 joule per K, or it has the value 8.6 into 10 raised to minus 5 electron volt per K. So one has to discuss the three different situations for this Fermi-Dirac distribution function. So if we consider E is equal to EF, first case, that is E is equal to EF. So by putting this value of E, one may write f of EF is equal to 1 upon 1 plus e raised to 0, as here EF minus EF is 0. So as we know, this becomes 1/2. So when the energy is equal to the Fermi energy level, then the energy states which are at Fermi level has the probability of 1/2 of being occupied by an electron. So this is the first case. Then we will discuss the second case, for which E is less than EF. And as we know, the Fermi distribution function is given by f of E is equal to 1 upon 1 plus e raised to E minus EF upon KT. And by taking E is less than EF as well as T is equal to 0. So if we put E is equal to EF, then this E minus EF become negative, and at T is equal to 0, this KT becomes 0. So one may have the value for this Fermi distribution function EF is equal to 1 upon 1 plus e raised to some negative value upon 0. And so as we know, some negative value upon 0 is minus infinity. So one may write this f of E is equal to 1 upon 1 plus e raised to minus infinity, and this value of e raised to minus infinity is 0, so we get 1 upon 1 plus 0, which is equal to 1. So the energy level which is below the Fermi level, there is the probability of finding the probability will be 1 of occupied by electron. That is, at the energy level, if Fermi level is in between these two, that is at the middle of this forbidden gap, then there is probability of finding the electron below this Fermi level, which is 1. That is, there is probability of finding the electron is more than that of the E is equal to EF. That is, at Fermi energy level, the probability of finding the electron being occupied at the Fermi level is 1/2, and the energy level which is below the Fermi level, there is probability of finding the electron which is equal to 1. Then we will discuss the case number 3. Which is E is greater than EF, and as we know, the Fermi distribution function is given by f of E is equal to 1 upon 1 plus e raised to E minus EF upon kT. So for this case also we consider T is equal to 0. So by putting these two conditions in Fermi distribution formula, so we will get f of E which is equal to 1 upon 1 plus e raised to some positive value, because here E is greater than EF upon 0. So we will get f of E is equal to 1 upon 1 plus e raised to infinity, and as the value of this 1 plus e raised to infinity is infinity, we get 1 upon infinity, which is equal to 0. So the energy level which is above the Fermi level, there is 0 probability of finding the electron, or the energy level above the Fermi level has a probability, that is 0 probability of being occupied by an electron. So by putting these three conditions, if we plot the Fermi distribution function as a function of energy, we will say So this is the condition for t is equal to 0. T is equal to 0. If the temperature is below the T is at T is equal to T1, so there will be some change in Fermi distribution function as a function of energy. So if this is the EF, then we will find some field state and some empty states. So these are the field state and these are the empty states. That is, at this there are holes, and this is the situation at T is equal to some temperature T1, and there are electrons and this is the situation at T is equal to T1, or these are the field state which are given by F of E. These are the field states. And further we change the temperature from T is equal to T1 to T is equal to T2, then again we find some variation with the Fermi function at T is equal to T2. So this figure explains the distribution function, that is Fermi distribution function, as a function of energy, and it is symmetrical about the Fermi level. So this is all about the Fermi distribution function and Fermi energy. Now we will see the electron and hole concentration. So the Fermi distribution function can be used to calculate the concentration of electrons and holes in semiconductor. If the densities of available states in the valence and conduction bands are known, and the electron concentration in conduction band is given by N naught is equal to integration over EC to infinity F of E into NEDE. This is equation number 1. So in this equation, this NEDE is nothing but the density of states in the energy range D, and the F of E is the probability of occupancy. So in this equation, the subscript 0 for electron concentration, that is N naught, or for hole concentration one may write P naught. So this subscript indicates the equilibrium condition. Thus the total electron concentration is integral over the entire conduction band, and as we know, the that is the density of states is proportional to e raised to 1/2. This NE is proportional to e raised to 1/2. Then this density of states increases as energy increases, or as there is increase in electron energy, the density of states increases. On the other hand, the Fermi function function becomes extremely small for the large energies, and the situation is given in this function, that is the density of states increases with increasing energy, while there is very small value for the f of E at large energies, due to which there shows the NED, the product NEFE is decreases above this EC. In each case, the product Fe into Ne decreases as energy increases. Similarly, as Fe is the available energy state, or Fe is the Fermi function, so the probability of finding the empty states is given by 1 minus f of E, and as f of E is the field states and 1 minus f of E is the empty states, so in this formula this Ne into 1 minus f of E also decreases below the valence band edge. So there is probability of finding the holes near the valence band edge. So this is all about the variation of NE, Fe and the carrier concentration as a function of energy. So as we have this equation number 1, which is N naught, that is electron concentration, which is given by integration of EC to infinity Fe into NED. So by integrating this equation, we get N naught is equal to Nc into F of EC. This is equation number 2, where this Nc is nothing but the effective density of states in conduction band. This is effective density of states in conduction band. In conduction band. So in this expression we assume the Fermi level f of E lies at least several kT times below the conduction band, and then the Fermi distribution function can be simplified as f of E as we know, this Fermi distribution function is given by 1 upon 1 plus e raised to e minus ef upon kt. Okay, so the Fermi distribution function in the case where the ef lies or Fermi level lies below the EC, so one may write in place of E, one may write EC. So f of EC is equal to 1 upon 1 plus e raised to EC minus EF upon KT. So this is equation number, or this is the Fermi distribution function, and we will see how this can be solved. So as EC is greater than EF, EC is greater than EF. So in this case, f of EC is equal to, as f of EC is equal to 1 upon 1 plus e raised to EC minus EF by KT. One may write this f of EC is equal to 1 upon e raised to EC minus EF by KT. Or one may write it as e raised to minus into bracket EC minus EF upon KT. So this becomes equation number 3. So since KT at room temperature has the value KT equal to 0.026 electron volt, as at room temperature this KT has value 0.026 electron volt. This is a good approximation, and for this condition the concentration of electrons in conduction band is given by NC concentration of electrons in conduction band N naught is equal to NC into e raised to minus into bracket EC minus EF upon KT. So this is equation number 4, and we have the equation number 3, which is f of EC is equal to 1 upon e raised to EC minus EF upon KT, which is equal to e raised to minus EC minus EF upon KT. So this is equation number 3. And this is equation number 4. So this equation number 4 indicates the electron concentration increases as EF moves closer to EC. So similarly, as this is the electron concentration, one may write the whole concentration, which is given by P naught is equal to NV into e raised to, or NV into 1 minus f of E, where NV is the effective density of states in valence band. This NV is effective density of states in valence band. So this is equation number 5. So the probability of finding the empty states in the valence band is given by 1 minus f of E. Probability of finding the empty states in valence band 1 minus f of E. So which is equal to 1 minus, as we know the Fermi distribution function is given by 1 upon 1 plus e raised to ec minus ef by kt. So one may write here 1 minus 1 upon 1 plus e raised to ec minus ef by kt and by solving this we get 1 plus e raised to, sorry, here must be ev, as we are finding the empty states so which are below the valence band, and by solving this we get 1 plus e raised to ev minus ef by kt minus 1 upon 1 plus e raised to ev minus ef upon kt. So this 1 minus f of e is nearly equal to, as this 1 get cancelled, it is nearly equal to e raised to ev minus ef upon kt. So this is next equation number 6. One minus f of e. So the concentration of holes in valence band is given by this equation number 5, which is Nv into 1 minus f of e, and we have 1 minus f of e is equal to e raised to ev minus ef by kt. So the concentration of holes in valence band is given by P naught is equal to Nv into e raised to ev minus ef upon kt. So this is equation number 7. So we have this equation number 4 and equation number 7, which gives the electron and hole concentration predicted, which are valid whether the material is either intrinsic or doped, provided that the thermal equilibrium is maintained. Thus, for the intrinsic material, EF lies at some intrinsic level EI, near the middle of band gap, and the intrinsic electron and hole concentration is given by Ni is equal to Nc into e raised to minus Ec minus Ef upon Kt. So this is the intrinsic carrier concentration, that is intrinsic electron concentration, and Pi is given by Pi is equal to Nv into e raised to minus Ei minus, sorry, here must be Ei, and here Ei minus Ev upon Kt. So these both are the equation number 8, and the product N0 and P0 at equilibrium is constant for particular material and the temperature, even if the doping concentration is varied. So one may write N naught into P naught, N naught into P naught, which is equal to into square bracket NC into e raised to minus into bracket EC minus EF upon KT into NV into e raised to minus into bracket EF minus EV upon KT. So this N naught into P naught is equal to NC into NV into e raised to minus of EC minus EV upon KT. But as we know, this difference between EC and EV is nothing but the EG, that is band gap. So we may write this N naught into P naught is equal to NC NV into e raised to minus EG by KT. So this is equation number 9. Also the product NiPi can be given as NiPi is equal to NC into e raised to minus into bracket EC minus EI by KT into NV into e raised to minus EI minus EV by KT. So one may write this must be capital N at each step. This must be capital N. So this product NiPi is given by NC NV into e raised to minus EC minus EV upon KT, and which is equal to NC NV into e raised to minus EG by KT. So this is next equation number 10. Product NiPi. So the intrinsic electron and hole concentration are equal since the carriers are created in pair. So we have Ni is equal to Pi. Okay, so thus the intrinsic concentration is given by Ni is equal to under root NC NV into e raised to minus Eg upon twice kT. By taking square root of this equation 10, we have this equation number 11, which gives the intrinsic carrier concentration and the constant electron and hole concentration in equation number 9, that is this N0 P0 is equal to Nc and V into e raised to minus Eg by kT can be written conveniently as N0 P0 is equal to Ni square. So this is equation number 12. So we have seen the electron and hole concentration which were given by equation number 4 and equation number 7 previously, and this equation number 11 gives the intrinsic carrier concentration. So this is all about the carrier concentration at the thermal equilibrium for doped and intrinsic semiconductors. So with this I conclude this lecture. Thank you.